This is our link equation lecture. It's lesson 4, the last lesson in our wireless communication portion of the TT&C technology section of the class. Previously, we've gone through the basics and fundamentals of radio frequency wireless communication, and then we talked about modulation as well as the use of antenna. Now we're going to talk about this thing called the link equation. The link equation provides an estimate of the quality of the wireless communication link. And it does this by computing a ratio known as the signal-to-noise ratio, which is the amount of signal energy there is in what we receive compared to the amount of noise energy. As you can imagine, we want more signal. That's the part we care about. And ideally, we want less noise. And if we do that, then the ratio of signal-to-noise becomes larger, and that's a good thing for us. Without going into the mathematics yet, our intuition tells us a lot about what's good and bad for the quality of our communication link. And there on the bottom right, you can see a whole slew of considerations and sort of if they're good or bad for us. So I can imagine broadcasting my signal with more power, and that's going to be good because I'm investing more energy in the portion of the link that I want, the signal. On the other hand, if I am broadcasting this over a much larger distance, and I know distance is going to mean that the energy gets sort of spread out the farther I go, then that's generally a bad thing. I'm going to lose energy per bit of my message with a longer distance. Alternatively, if I use a high gain antenna with a good gain, a good focusing of the power, that tends to be good as long as I'm pointed in the right direction. And on the next line, you can see if I have improper antenna pointing, well, that would be bad because I'm going to have a loss in the direction that I'm trying to convey my message, and so on and so forth throughout this list. The link equation itself is a favorite of mine. It's one of the most interdisciplinary equations in all of engineering. It truly does have terms that represent all the different disciplines that we tend to deal with. For example, you can imagine transmit power, and even the quality of our connections and components, and those are electrical kinds of considerations. When I think of the size of my antenna and how well I need to point it mechanically, that's a mechanical kind of topic. If I'm thinking of encoding techniques and data rates, those are things that often computer engineers talk about. And then there are even parameters that have to do with things that are going on in my environment, like the atmospheric conditions and other communication broadcasters and things like that. So the link equation itself is this notion of signal-to-noise ratio, but a little more precisely, it's the energy in 1 bit of communicated data divided by something called the received noise density. This is sort of our expression of noise. You can see our equation there, which may not make a lot of sense here to begin with, but there it is. So we're going to derive it, and we're going to explain every single one of those terms. But to get started with, we see EB divided by NO. That's energy per bit divided by received noise. And you can see the definition of the terms there below the equation, and you can see things like transmit power and my transmitter antenna gain, my receive antenna gain, and so on. Before we go through where that equation comes from, it's worth noting that in addition to the form that you see there at the top, which is sort of the ratio form with all my terms multiplied or divided by each other, oftentimes we use this notion of decibels and we convert this equation. We apply the decibel conversion to it. And when we do that, that log 10 function in the definition of decibels will turn multiplication and division into addition and subtraction. And sometimes we'll find that that's an easier way to perform the link analysis. So you'll see both of these expressions used. You may wind up using both depending upon the situation. They're equivalent to each other. They're just different ways of expressing the same relationship of energy per bit divided by noise. So here we are going through the beginnings of the derivation of this equation. I'm not going to go into an exhaustive discussion of each term, but we can walk through most of them, and I think you'll start to develop your intuition for where these terms come from. we start with the notion of I'm sending this string of ones and zeros from one location to another, and I'm using a certain transmit power. So I'll begin with the transmit power, and in the second line, I'll recall that as the signal spreads out from our nice isotropic antenna, it spreads out on the surface of a sphere, so to speak, and the farther that signal goes, the more the energy is spread out over the surface of a larger and larger surface area. And so I am losing energy per unit area on the surface of the sphere. And so that goes as an inverse square law. And so you see that term thrown in the second line. And in the third line, we say to ourselves, well, maybe we're not using an isotropic antenna. Maybe we're using an antenna with gain. And so I have a ratio of how much power I'll be receiving, assuming that I'm pointing in the right direction. And for now, we'll make that assumption. We'll take pointing losses into account later on. And so in the third line, I have this notion of the increase in power that I receive because the transmit antenna has the focusing ability that gives it gain. And then in the last line on this particular slide, I say, well, I'm going to have an antenna with some sort of effective area, and it's going to receive some portion of the surface area of this beam. And so for now, we'll put in a placeholder of the effective area of the receive antenna. And what that gives us is the power received there on the bottom line is equal to the transmit power times the gain of the transmit antenna. And then I have a dividing expression, which is my inverse square law. Then I'm going to multiply this by the area, the effective area of my receive antenna. So far, I now have an expression for the received power at the reception antenna. I'm going to use that expression. I'm going to move that to the top of my next slide. And going from the top line to the middle line on this slide, what I'm going to do is I'm going to go and find out the expression for the effective area of an isotropic antenna. And right now I'm assuming my receive antenna is isotropic. And it turns out that that expression is what you see there at the right and what I've used to substitute into our main expression there. But that's the speed of light squared divided by 4 pi times the frequency that I'm using for communications squared. So that's my radio frequency there in the denominator. And that's nothing that we've talked about before, but that's something in antenna theory that is an interesting factoid. So we've plugged that in. And then I say, well, that was for an isotropic receive antenna. And just like we might have gain on our transmit antenna, we might have gain on our receive antenna. And so in the last line, we're putting that in as well. So now I still have an expression for the power received at my receive antenna. I'm going to take that bottom expression and move it to the top of the next slide. And there it is. And in our next step, I'm going to take most of that, the c squared and everything in the denominator, and I'm going to define that as my path loss. And so this really, for the most part, comes from the inverse square sort of path loss with a few other factors thrown in. You'll see that that loss is frequency dependent in this case. But I'm going to replace that expression with the parameter L sub s, which is representing path loss. So at this point, I have my received power at the receive antenna is equal to the transmit power times some factor for the gain of my transmit antenna, times some factor for the gain of my receive antenna, and times some factor which now is presumably less than 1, which is a loss for the fact that I'm traveling over a certain distance. And here, my next step is I'm going to consider a number of other loss sources. And really what happens in practice is you determine which ones really are relevant, have an impact to performance for you, and you add in these extra terms. And you may or may not add in all of these. You may add in some other ones depending upon your particular situation. In this case, I've added 4 terms, and the first 2 are L sub theta t and L sub theta r. Those represent the antenna pointing losses for my transmit antenna and my receive antenna. And then the third one, L sub A, is a loss due to the absorption of energy through the atmosphere. This might be through the atmosphere, particularly if there's rain or fog, which makes it worse. We'll talk about how to get these numbers later, but I have a placeholder for losses due to those kinds of effects. And the last one is a line loss. So that's just losses going through cabling and connectors and things like this. So there's my expression at the top. Again, this is now a nice long convoluted expression for receive power. But really what I want is energy per bit. And so to make the leap from one to the other, I realize that power is energy per unit time. And we have a transmission data rate, which is bits per second. And so to get the energy in any one bit, I have to take my receive power and divide by my data rate. So there in the red circle at the bottom of the slide, you see energy per bit equals my receive power divided by my data rate. What that means is the higher your data rate for a given receive power, the less energy goes into any one bit in your communicated message. And so to the right, you see the full expression, everything on the top there, and with the capital R representing data rate there in the denominator. Now what I'm going to do is I'm going to throw in noise. Really what I want is this notion of signal noise, which is energy per bit divided by noise. My expression for noise, which I'll break out later, but for now we're going to say that noise is proportional to something called the system temperature. And so you see a constant proportionality there, K times T sub S, which is my system temperature. Turns out K is Boltzmann's constant. And we'll talk about how to get T sub S here in a few moments. But at this point, I have my full expression for the purposes of this lecture, and recall my comment about how you may or may not add additional terms or even remove some of the ones that are here depending upon your particular situation. So for example, if you have two antennae that are pointed mechanically to each other and they're installed that way, or if you have omnidirectional antenna, you might drop the gains. I mean, presumably the gain is still in there, it might just simply be a 1. But it's up to you to figure out how to wield the power of this equation. So here's my equation, and I have it in both forms, the standard multiplicative form as well as the decimal form, which breaks things out as additive terms. And there are all my definitions of each term as a summary of how we got the equation in this particular form. And when we use the link equation to do analysis of communicating wirelessly with a spacecraft, we have to realize that some of the parameters of the equation may change over time, and not just over the course of weeks or months during different contacts, but also even during a single contact as the satellite flies overhead. And so in this graphic, you can see a couple obvious parameters that are implied by the graphic and also listed here in the sub-bullets. But certainly the distance to the satellite from the ground antenna may change as the satellite flies overhead. Traditionally, the satellite comes up over the horizon, it's very far away. And when it flies overhead, relatively speaking, it's much closer, and then it gets farther away as it settles, and we lose sight of it over the next horizon. During that time, close to the horizons, the atmospheric losses can be greater because we're going through more of the atmosphere. The way the sort of the geometry and kinematics associated with tracking make it such that we often have greater pointing errors when the satellite is at much higher elevations rather than when it's low on the horizon. Another factor is the antenna noise will change. As we scan across the sky, you can imagine scanning across the sky looking at the satellite, and if the backdrop is the sun, well, the sun is this big emitter of electromagnetic radiation, primarily in the visible range that we see, but it also emits in the microwave range, and so that looks like a noise source to us. And so that will come and go depending upon where it is relative to where we're pointing the antenna. So the point is that a lot of these parameters change during the course of a contact, and then certainly longer term as well. And we need to be aware of that so that we can perform the analysis that's appropriate to the answers we're trying to find. So the next few slides kind of walks through and says, how do I find this term? What number do I use? Some of the terms are very straightforward because they're specs or they're settings when we run a contact, and some of them are a little more difficult to find. In some cases, we never really know exactly what they are, so they're estimates, or we use an estimate because the cost to figure out what the real number is might be difficult. So then you could imagine throwing in some safety factors and things like that. And so I'm going to pretty quickly go through these 6 slides. We'll talk about the sources for how to get the numbers for all the parameters a little more in the in-class section. But to get started, here's a whole set of parameters that are in the link equation. Most of these are pretty straightforward. So for transmit power, winds up being whatever the transmit power is on our transmitter, and presumably we're controlling that, so we know what that number is. We also know what data rate we're using to communicate, so that's a number that we have control over and certainly knowledge over. Boltzmann's constant is right off the shelf. That's a known constant, so we can use that. The antenna gains, both on the transmit and the receive side, are something that we probably spec'd out to begin with. But either way, we have committed to using a certain antenna, and we certainly should know sort of spec sheet kinds of numbers for that antenna. And those would include the gains. The path loss itself, well, we know the distance, and maybe that distance changes, so we might have to do this at a couple different points in the orbit. But we have some notion that at a certain point we have a certain geometry, and that implies a certain range or distance between the transmitter and the receiver, so we know what that distance is. And we also know what frequency that we're using to communicate, so we can plug those numbers in. Line loss, a lot of times you can actually go up and measure your line losses. And sometimes we just estimate it, and it's very typical to say, well, there's sort of maybe a loss of 1 dB through the line, maybe a loss of a dB or 2 through each connector. And so a lot of times it's a bit hand wavy, kind of rules of thumb. Typical measurements we've seen elsewhere are used, and we might do that without actually making an estimate. Particularly early on, when we're using the link equation to do sort of rough sizing in the conceptual design phase, we haven't built anything, so I can't make a measurement. So we'll throw in some WAGs based on prior experience and other things that we've seen in order to come up with an estimate for line losses. Usually it's a few dB. For antenna pointing errors, we would need to understand how precise, kind of what the performance is of our antenna pointing system, and then how that couples with the beam pattern of the antenna that we're using. So you can see here, if you recall, this is the one of the beam patterns, of one of the slices of the SRI 18-meter dish, and we know that the gain of this is very high, but in this particular case, I'm interested in knowing what the cost is of not pointing perfectly. And a typical thing to do is I would say, well, what is maybe the worst case control that I have over antenna pointing? And that number is whatever it is. We get that from a spec, but some of the equipment that we use at Santa Clara, it's maybe half a degree. And so I might play a sort of worst case analysis game and say, well, at half a degree of pointing error, let's read off the loss directly off the beam pattern. And that would give us an idea of maybe the worst case loss that I would face in terms of pointing the antenna. So we can do that for both the receive antenna as well as the transmit antenna. For the absorption loss, that's the loss through the atmosphere, and the nature of the atmosphere certainly affects that. So the differences in the atmosphere, if there's a very clear sky versus if it's foggy or rainy or cloudy, and they're curves. There's empirical data that gives you common numbers for what the losses are in each of those situations. And so oftentimes you would go to those curves. A couple of examples are here on the slide, and I'm not really asking you to read those numbers off right now, but the idea is that there are plots, there's data available. This isn't done by analysis. This is done by someone who's made these measurements and made the measurements available to you, and you can use them to have some idea of approximately what absorption loss is for each of these conditions. And you may run the link analysis several times. You might have an analysis for clear sky. You might have a worst case analysis. of a lot of fog. Um, so it's up to you in terms of how you want to run the numbers. System temperature has it's a bit of a difficult thing to wrap your mind around in some cases. We typically break it into two parts: the noise that comes from our own equipment, as well as the noise that comes from external sources that we pick up through our antenna. And so the internal noise comes from the fact that we don't have perfect equipment. We get distortion of the signal as it moves through our equipment. Um, the equipment has the equipment is operating at a certain temperature, and something I think I've mentioned before, and I'll certainly mention again, is any object with a temperature radiates electromagnetic energy, and that's sort of our understanding of black body effects. And I mentioned before, say, the noise, and we're going to see that the noise from the sun as an example. So the sun is at a temperature; it's a very hot temperature, um, and so it has a spectrum of radiation, and we're used to thinking of the sun in terms of the visible range because that's what we see. But it's a very sort of broad spectrum emission that you get from black body radiation, and part of that radiation comes off in the microwave range. So anything with a temperature is emitting radio waves. Now, it may be very small amount, a very low amplitude, low energy kind of wave, but it's radiating across the spectrum. So the portion of that near the range in which we're receiving, we're going to pick up some of that, and that's not the signal we're looking for. So that's a source of noise. So some of this noise comes internally, and in particular the receiver itself. That's probably our primary piece of equipment that's doing the reception job, and it has an equivalent noise temperature. Now, this is not the temperature we think of if we put our hand on it and it feels hot. This is a different temperature. This is a temperature associated with um, the noise that it generates in the radio frequency range, in the microwave range. So when you get a receiver, a lot of times on the spec sheet they'll either tell you the equivalent noise temperature of the receiver, or they may give you another factor called the noise figure. And there's an equation we use that you see there in the last sub bullet that if I have the noise figure, I can go through a process to compute the equivalent noise temperature. And so that's again sort of ultimately it's a piece of information we get off a spec sheet, and we plug and chug in terms of the relationships that we use to do the analysis. Those are the internal sources. We also have external sources. So this is the antenna that presumably we're pointing toward the satellite. The satellite's emitting, and because it's emitting, we're going to receive some fraction of that energy. But there are other things out there in the sky that are emitting as well. And in fact, they may be emitting directly into the antenna, but remember those side lobes, we have these other little directions in terms of the geometry of the spacecraft, these other directions in which we might be picking up a reasonable amount of energy, with a little bit of gain. So we have to sort of think about it from a 360-degree perspective, or a 4 pi sterdian perspective. And we assume, here are the other things that are broadcasting, and we have to take those into account. And sometimes what we do is we put together sort of an average, gain-weighted temperature of the noisy objects. And this may change depending upon the pointing of the antenna. In fact, it definitely will change. So if I am on the Earth and I'm pointing the antenna toward the satellite and the satellite flies in front of the sun, then I'm going to have a significant noise figure to deal with because the sun is putting out an ample amount of radio frequency, sort of microwave range energy. Conversely, if I'm on the satellite, I'm antenna on the satellite, and the satellite's pointed to the Earth in order to communicate, well, the Earth is radiating in black body, and it has a temperature. And so I would take that system temperature into account and go through this analysis. So we think of some of the major noise sources, which might be natural bodies that have a non-zero, non-absolute zero temperature. They may actually be other spacecraft that are transmitting anywhere close to our frequency. They may be other transmitters in the air that aren't on spacecraft. They might be terrestrial sources. TV news vans was one of the concerns we have with the S-band system that we use with GeneSat. So you have to sort of put yourself in the context of the problem you're working, determine what those noise sources are, try to identify as many of the significant ones as you can, and then come up with some sort of estimate as to how much noise that they are producing. So based on that and based on the internal noise temperature, you can put together kind of an overall estimate of what the system noise temperature is, and you use that in the link equation. And here's some examples of some empirical sources for things like celestial bodies and things like that. These are the numbers that you would typically find. And again, I'm not overly concerned specifically what the numbers are right now, but the point is there are resources. There's data available that tells you what some of these equivalent temperatures are. Okay, so we're almost done here. We've gone through this big, long discussion of the link equation. We talked about what the terms are, how the equation got formed, kind of what its derivation was, where to find the information for each parameter in order to actually execute and compute signal to noise. Let's say you've done all that. And so now you have a number, you have a ratio, you have the signal to noise is such and such, and let's say we've computed in decibels. So we've got a number. The question is that good enough? What does that have to be in order to be good enough for me to reliably interpret the information on the radio waves and to do demodulation and everything else? So what value of signal noise is acceptable? I have a tool to compute it now, but I'm not quite sure what number is the right number. I know how to adjust it. If it's too low, I can increase the power, I can increase gains, I can lower losses. But to what extent do I need to do that? I don't know what my threshold is. So figuring out that threshold is really important. And this is certainly something we will review during the in-class session. But to give you an idea, it depends upon how many bit flips you're willing to take. The worse the quality, the more bit flips you're going to have, the more noise will corrupt the digital information. And remember, we talked about we went digital, we went discrete to be immune to noise. But if you have a high enough level of noise, it will even corrupt digital data. And the more noise, the more that corruption. So part of that is how many bits per thousand do you want to suffer bit flips. Then another thing that we can associate with this is what coding technique, what modulation and coding technique are we using? And if we're using techniques that allow us to do error detection and correction, well, then maybe we can deal with a higher bit error rate in terms of the raw bit flips because we have a coding technique that allows us to correct for those. And so that somehow plays a role here. And then there's the margin of safety. So I might come up and say, well, here's the signal to noise that gives me a certain bit error rate given this coding technique. And then we need to admit to ourselves that we've had some error sources come into our analysis. So we throw in a margin of safety. So how much of a margin of safety do you want? And oftentimes in spacecraft programs, that's actually a required value, a specified value. So you'll be told that as a rule of thumb, our program uses 3 dB margin of safety. And so that's going to be a requirement to you as a communication systems engineer that you need to make sure that we get whatever the acceptable signal noise is, plus another 3 dB as a margin of safety. So here's an example of a diagram that links these things together. So what we have on the horizontal axis is signal to noise. And so you can see that number computed in decibels. And on the vertical axis, we have bit error rate. So up at the top, we have horrible links. You see 10 to the minus 1. So that's 1/10 of our bits are errors. So every 10 bits, we got a bit flip. And that would be a pretty bad link. Lower down, you see 10 to the minus thirds, that's 1 every 1,000, and so on and so forth. So better performance is lower on that scale. So we have bit error rate on the vertical axis, we have signal to noise on the horizontal axis. Better signal to noise generally is a good thing, so moving to the right is good in that particular plot. And then we have a bunch of curves, a bunch of lines that have been plotted. And each of those lines is for a different flavor, different combination of modulation and data encoding. And if you look way out to the rightmost curve in the upper right-hand portion, that is non-coherent frequency shift keying. And relatively speaking, that's not a very sophisticated way of communicating. move over to the left a number of curves, you see one example, if I'm down in the lower left-hand portion, kind of the third plot to the right is something that's the arrow shows. It's called convolutionally coded PSK, or phase shift keyed. And if you remember in command and data handling, we talked about convolutional encoding being an error detection and correction technique. And the R and the K values gives you some specs on the convolutional encoder in terms of its structure. But if you use that, then you can detect and correct some of the bit flips. And it shows you a different relationship of performance. So just to pick off a couple points, if I wanted 1 in every 100 bits to flip, if that was okay with me, then I'm operating at the 10 to the minus 2 horizontal line. And if I move over all the way over to the non-coherent frequency shift key curve all the way to the right, and if so here I'm moving all the way over to the right to the frequency shift. And if I roughly move down, that wasn't perfectly vertical, but I'm kind of in the area where I need, say, let's just call it 10 dB of signal to noise in order to make that work. However, if I also want to have 1 in 100 bits flip, if that's okay, but I'm now using convolutionally coded phase shift keying, then I'm going to move across to that curve. As I come down, I'm sort of in the 4 dB range. So that means that I don't need to have as good a communication link. I need only 4 dB compared to the 10 dB, but I have to use a convolutionally encoded phase shift keying system, which is more complicated and more expensive, but higher performance. So I have a trade-off. I can use a less sophisticated system and just have a more powerful signal noise ratio, or a more sophisticated system and a less powerful signal noise ratio. And you can go through all sorts of trade-offs um, using these relationships captured in this particular plot. I can do the same thing, say at 10 to the minus 4 or 10 to the minus 5. I will tell you that it's not even on this chart, but 10 to the minus 6 is kind of a benchmark for most communication satellites. Certainly the ones that I've worked on, 10 to the minus 6 is continued at an acceptable bit error rate, and probably even lower than that currently. And this gives you that relationship between acceptable bit error rate and the signal to noise you need to achieve it as a function of your selection for modulation and data encoding. And then whatever you need for that, we tack on the margin. So if I am 10 to the minus 2 bit error rate is acceptable, and I'm using convolutionally encoded phase shift keying, and I require 4 dB signal to noise. If I have a requirement of 6 dB link margin, then that means I need 10 dB in order to achieve this. Okay, so I need to engineer my communication system so that I have a signal noise of 10 dB, and that gives me the required 4 dB based on this chart, plus a margin, an extra 6 decibels. So here are a few more examples if you want to go and practice this. I'm giving you a couple different data points. The first one, I'm requiring a certain link margin. I'm giving you the error rate. And I'm telling you that we're using convolutionally encoded PSK. I'm asking you what signal to noise do you need. If you look at that exercise, hopefully you come up with about 10.2 dB. Then it's twisted around a little bit. In example 2, we give you the modulation and encoding. Until you need a link margin of 3 dB to the minus 4, and asking you, in that case, what signal noise do you need? So you can go through those 2 examples and see if you can reproduce these numbers, and we will double check those in the in-class portion of the course as well. So usually when we do this analysis, we use a spreadsheet. It's called a link budget, and this allows us to trade things off. We've been told achieve a certain link margin. We have a certain requirement for bit error rate. As designers, we get to maybe choose the modulation and encoding technique, or maybe we fight back and say, given the money and what we can afford, we might not be able to achieve this in any way, and we might go back and try to renegotiate the specs. But once we have those specs down, now we can trade off things like, well, if I need better um, link margin or a better signal to noise, what should I do? Should I increase transmit power, or maybe buy a bigger antenna with a larger gain, or maybe tighten up my pointing system so I can get achieve pointing with less pointing error? Or maybe do I hop to a different frequency so my space loss is different? All those parameters in the link equation sort of spell out an option that I have in order to re-engineer the communication link. And I can play the game of running through different scenarios and trade-offs through the use of a spreadsheet. And in this spreadsheet, you see most of those terms down the left-hand side. In some cases, you see the contributors to the terms, and sort of under the hood, we're computing what the terms are in lower lines. And then in the columns, the last four columns, you see that we're basically running the numbers at different elevation angles with respect to the local communication station on the ground. And because of that, different elevation angles and a different altitude of the orbit, we get different distances to the spacecraft. And so we're running four different cases at a 0 degree elevation above the horizon, 10 degrees, 45, and 90. And so this sort of allows us to sketch out performance as we move through the orbit. So this is something that we will practice during the in-class section. We'll show you some of the real spreadsheets that we've used for some of the NASA missions and walk you through a few of the typical trade-offs that we have to do, both in the design phase as well as in the operations phase, and we're using this. So that's the end of our video for the link equation. A couple points to certainly remember. We're using this equation to assess the quality of a wireless communication link. It's a very interdisciplinary equation in the sense that the parameters that it uses to make this computation come from the electrical world, the mechanical world, the computing world, from the environment that through which we're transmitting information. All those things are things that are considered by the link equation. In the design phase, the equation allows us to trade off parameters like what frequency should we use, or antenna gain, or pointing, or power level, and we can figure out what the right blend is for our particular mission. And then remember that ultimately, once we compute signal, we need to figure out how that trade-off is with respect to the bit error rate and our encoding technique. And we're going to tack on some safety. We're going to tack on what's known as the link margin. That's the extra signal to noise that we desire in order to have this safety margin to ensure solid communications. It's very typical that we use numbers like 3 or maybe 6 dBs of margins for the kinds of missions that we're operating. That's the end of our video, and that actually also concludes the 4 lessons in the wireless communication portion.